Hi, this is Patel. In this lecture, we are going to understand the concept regarding the elements subjected to principal stresses. Now, whenever a body is subjected to any kind of a stress, we need to find out its normal, its tangential stresses, and its resultant stress. Later on, whenever we locate a principal plane, then we will be able to identify the direct stress which is acting on that particular plane. So first we are going to derive an equation for the general condition of normal and tangential stresses. First we get it, then we will apply the principal plane condition into that, and we will derive another equation for the principal stress and principal planes. So let's get started with the first derivation that I'm talking about. That first derivation is related to an expression for normal and tangential stresses on the plane at some angle when a general two-dimensional stress system is considered. Now, whenever I say a general two-dimensional system, what does it consist? It consists of two-dimensional direct stresses which are perpendicular to each other. Let's say if one stress is going in a horizontal direction and the another stress is going in a vertical direction, then these two stresses are a part of the two-dimensional stress system. Also, in this stress system, there might be a shear stress or a tangential stress. So altogether, these three force stresses in any direction can form a two-dimensional stress system. So let's assume that the body is subjected to all three types of the stresses. Whenever in a practical condition, if there is one or two stresses are missing, then we can put the value of that stresses as 0 in our equation. So this way, we are going to derive an equation in a general manner. Otherwise, whenever we derive equation for particular one stress, it will not be applicable for the practical application where single stress is not applied. So let's see our diagram of the body. Let's say this is our body. It has the rectangular shape. This might be any shape. It may be of a triangular shape or a square shape, circular, anything. But we are taking one example of a rectangular body. So let assume that this is the ABCD body, which is subjected to a two-dimensional general stress system, which consists of sigma 1 and sigma 2 two direct stresses and tau 1 shear stress. All the things we have listed it out on your screen. Now theta is an angle of the oblique plane EF, just like the plane that we have studied in the previous lecture. If you have not seen, I recommend you to watch that video so that you guys can understand the derivation, or the steps that we are going to use in this slide are explained in the previous video. So derivation will require that concept also. So let's move on for the next steps. First of all, what we are going to do, we are going to find out the horizontal force acting on the AD. Now what is AD? AD is nothing but a vertical face that you can see over here. This is our vertical face AD. Now we need to find out the horizontal force acting on the AD face. Now what is the horizontal force? Let's say that we name it as a P1. P1 is our horizontal force. Then it will result from this particular stress. So the stress is sigma 1. Stress equals to force upon area. So force equals to stress into area. So the stress equals to sigma 1 into area AD. Similarly, if you want to find out the vertical force acting on the AD, then P2, we name it as a P2, equals to shear stress tau into AD. Why is it so? Because on the AD plane, tau is also acting. There are two different stresses acting on the AD plane, that is the sigma 1 and tau. Now let's consider GF plane. What is GF plane? This one. Why we have taken this only, particularly this plane? Because it is horizontal and it is the part of the triangle that we are intended to find out of EF. We are focusing on this particular plane only. We are focusing on EF plane. So that's why, let's say we are intended to find out horizontal force acting on the GF plane. So on the GF plane, which stress is going in a horizontal direction? This one, tau. So again, P3, let's say it is the horizontal stress, P3 equals to tau into GF. Similarly, if you want to find out the vertical stress, then this stress is going in a vertical direction. So P4 equals to sigma 2 into GF. So this is how we have calculated each and every forces, not stresses, forces. Now what we are going to do, we are going to resolve all these forces in two particular directions. Which directions? That you need to see over here on the diagram. We are focusing on EF plane, this plane, right? I hope you all guys can see this annotation. We are focusing on this plane only. So there are two directions. First one is the perpendicular to the plane, which is like this. This direction is perpendicular to the plane. This is perpendicular. This direction is perpendicular to the plane. That is sigma n. And second direction is parallel to the plane. So this will give us a tangential direction. So first one is the normal direction and second one is the tangential direction. Let me remove unnecessary annotations because there is too much. Okay. So basically we are intended to resolve our forces in the two direction. First one is perpendicular to the direction and the second one is parallel to the EF plane. So let's say we are focusing on the PN force, which is in the perpendicular direction. So Pn is the resolution of all the forces. Let's say if we resolve the P1 force, then P1 into cos theta. Why is it so? Because P1 is in the horizontal direction. So in the horizontal direction, we will take it as a cos theta. P2 is in the vertical direction. So P2 sin theta is our resolution in EF direction. Similarly, P3 cos theta is horizontal and P4 sin theta is vertical. If we want to resolve all these forces in the tangential direction, then it will be represented by PT. Let me correct myself. This is PT. This is T value. T for tangential. So in the tangential direction, we will take it as a particularly opposite. So we have taken P1 cos theta in the normal direction. So in this direction, we are going to take it as a P1 sin theta. Now, if you remember, then P1 sin theta will be in this direction, tangential direction. So it is going in this manner. So what do we do now? So we need to find out that which force is going in this direction, let's say inclined downward, and which force is going is inclined upward direction. So this one is going in this manner. So P2 will definitely go in the opposite direction. That's why we have taken it as a negative. This is in the same direction, so it is a positive, and P4 is going in opposite direction, so it is negative. So while resolving the forces in the tangential direction, you need to keep the direction in your mind in order to do the algebraic sum. So this will help you to find out the normal forces and tangential forces. So what are we going to do? We are going to calculate a normal stress using the basic formula. What is the basic formula? Stress equals to force upon area. What is force? This is our normal force. This entire bracket is our normal force upon area. Area is EF. Now if we divide the EF individually with each and every component, then it will look like this. Instead of P1, we can write sigma 1 AD that we have seen in the previous slide. Instead of EF, AD upon cos theta, as we have studied in the previous lecture. Now, if you take this cos theta in the denominator, it will be sigma 1 into cos square theta. Similarly, if you take all the things in the nominator, all the denominator part in the nominator like this, then it will look like sigma 1 cos square theta, tau sin theta cos theta, tau sin theta cos theta, and sigma 2 cos sin square theta. So this is how we have calculated the sigma n1. Further, if we simplify this particular stress, then we can simplify it by doing so that instead of the cos square theta, we can write 1 plus cos 2 theta upon 2. That is basic trigonometry equation that we have studied in our 11-12 standard. Later on, you will see that tau sin theta and cos theta are repeated 2 times. That's why we have written 2 times tau sin theta 2 theta, and we have kept sin square theta as it is. So we we will use this trigonometry notation in the next step. So you will see instead of sin square theta, 1 minus cos 2 theta is used. Now sin theta, 2 sin theta and cos theta is another sin 2 theta trigonometry. If you multiply it individually, then it would look like this, and simplify it further, then your equation would look like this. So this is our normal stress on any inclined plane, whether it is inclined at a 90 angle or 60 or 0. You can find the normal stress on any inclined plane using this equation, provided your body is subjected to generalized two-dimensional stress system. As far as two-dimensional stress system is concerned, this is the master equation to find out the normal stress. Using this equation, you can find any normal stress in any case. So this equation is the master equation. You need to keep this in your mind. Similarly, we are going to derive the equation for the tangential stress. So for the tangential stress, we are going to use the same formula, force upon area, but instead of the normal force, we are going to use the tangential force. Similarly, if we use the same trigonometry formula and simplify it, then our tangential stress would look like this. So these are the two basic equations that you need to understand, or that you need to mug up literally in order to solve the examples. Directly we will apply these equations whenever in your example it is required to calculate a normal stress or direct stress or a tangential stress. So whenever it is asked to find out the resultant stress, we are going to use this formula. So this is how we have derived our formulas. Now what we will do, we are going to find out the location of the principal's planes. So once we find out the principal plane location, instead of theta, we are going to put that particular angle of principal plane. And further, we will simplify this equation to find out the principal stress or the direct stress acting on that plane. So we have already derived that particular formula using the Mohr circle, and this is the list of the formula that you need to understand for our example. So there are basically two types of the principal plane, major principal plane and minor principal plane of major significance. Intermediate plane is generally not asked. So for the major principal plane, the stress which is acting on that plane can be written as the sigma n1, and for the minor principal plane, the stress which is acting is considered as a sigma n2. So sigma n1 and sigma n2, both equations are almost similar except this sign. Here it is a positive and here it is a negative. So both the signs are different except that both the equations are almost same. Whenever maximum shear stress plane is asked, then you can find out the maximum shear stress using this formula. Now in order to locate the principal plane, we need to find out this formula, that tan 2 alpha 1 equals to 2 tau upon sigma 1 minus sigma 2, where you will see alpha 1 is the angle of major principal plane with vertical, and alpha 2 is the angle of minor principal plane with the vertical. So this is how we are going to locate our principal stresses. On the left, that you have, whatever you are seeing over here is a Mohr circle. Mohr circle is the graphical method that we are going to use in the upcoming chapter. But using this method, we have located our principal planes. So we will move forward for sign conventions. So first of all, consider the sigma 1 as the major direct stress or the bigger value, sigma 2 as the minor direct stress or the smaller value. Generally, we will term it as a sigma n1 and sigma n2. But here we are looking at the sign convention. For that, not generalized equations or terminologies are required. So first of all, let's the theta is our angle of inclined plane with the vertical, with the plane of sigma 1. Tau is the shear stress. Take sigma 1 as always positive. So which one we will take considered as a sigma 1? The value which is bigger one. So the bigger value is always considered as a sigma 1 and smaller value is considered as a sigma 2. So we will consider sigma 1 always positive, whether it is a tensile or a compressive. Keep this in your mind. After that, sigma 2 is similar. If it is similar to sigma 1, then sigma 2 is also positive. But if sigma 2 is opposite to sigma 1, then sigma 2 is considered as a negative. So this is the basic sign convention that you need. Now let's say angle sign convention. We are here for the angle sign convention. So if we are measuring the angle in the clockwise direction, then it is considered as a positive. If we are measuring the angle with the reference vertical line in an anti-clockwise direction, then it is considered as a negative. Then tau. So whenever you are seeing the tau value in this manner, on the left side, if left corner, if it is merging over here, and on the right corner if it is merging over here, then this type of shear stress is considered as a positive. On the opposite note, on the left side, if it is merging over here, and on the right side if it is merging over here, then the shear stress is considered as a negative. So this is how the sign convention works. This sign convention will be helpful to you while solving the examples. So keep this sign convention in your minds. Keep practicing your equations, and we will apply those equations in our examples in the upcoming lecture. Till then, thank you.